sklearnlinearmodelLasso. Description: explain in detail. Lasso least absolute shrinkage and selection operator is a linear model that uses L1 regularization to perform feature selection and avoid overfitting. It adds a penalty to the sum of absolute values of the regression coefficients. This penalty encourages smaller coefficients and even forces some coefficients to be exactly zero, effectively removing the corresponding features from the model. Lasso is particularly useful when dealing with high-dimensional data where many features might be irrelevant or redundant. Inputs: X a 2D array containing the training data features. Each row represents an instance, and each column represents a feature. Y a 1D array containing the target variable values corresponding to the training instances in X. Outputs: Core a 1D array representing the learned regression coefficients for each feature. Intercept: the intercept term of the linear model. Steps: initialize the regression coefficients often to 0. Iterate over the training data, updating the coefficients using a gradient descent-based algorithm. During each iteration, the algorithm also calculates the L1 penalty term and adds it to the overall cost function. The algorithm continues to iterate until convergence, meaning that the changes in the coefficients are below a certain threshold. Metrics: mean squared error MSE measures the average squared difference between the predicted and actual target values. R squared represents the proportion of variance in the target variable that is explained by the model. Mean absolute error MA measures the average absolute difference between the predicted and actual target values. Visualization plots: coefficient plot: a bar plot showing the magnitude and sign of each feature's coefficient. This plot helps visualize the feature importance and identify features that have been effectively removed by the Lasso model. Residual plot: a scatter plot of the residuals, the differences between predicted and actual target values against the predicted values. This plot helps assess the model's assumptions and identify any systematic deviations from linearity. Fine-tune parameters: alpha regularization strength. A higher alpha value leads to stronger regularization, resulting in more coefficients being forced to 0. Fit intercept: Boolean flag indicating whether to fit an intercept term to the model. Normalize: Boolean flag indicating whether to normalize the input features. Uncertainty methods: confidence intervals calculated for the regression coefficients to estimate the uncertainty in their values. Bootstrapping: a method for estimating the uncertainty in model predictions by repeatedly sampling the training data with replacement and fitting the model to each sample. Challenges and fixes. Challenge 1: choosing the optimal alpha value. Sample use case that resulted in challenge 1: setting alpha too low may not provide enough regularization, leading to overfitting. Setting alpha too high may remove too many features, resulting in an underfit model. Fixes to challenge 1: use cross-validation techniques, e.g. grid search CV, to systematically search for the best alpha value that balances bias and variance. Challenge 2: handling highly correlated features. Sample use case that resulted in challenge 2: when features are highly correlated. Lasso may arbitrarily select one feature from the correlated group while setting the others to 0. Fixes to challenge 2: consider using feature selection methods, e.g. PCA, before applying Lasso to reduce the dimensionality of the data and address collinearity issues.